Hey, good evening, everyone. This is Robert Haynes with the National Weather Service in Burlington. We will get started in a couple minutes to let people come in. We're expecting about 7 people tonight, so we'll get started in just a couple minutes. All right, I guess we'll go ahead and get started. We'll see if we have a few people arrive late. Otherwise, it looks like it might end up just being the 3 of us tonight. Again, my name is Robert Haynes here, and I work here at the National Weather Service in Burlington as a forecaster. And I work with the Skywarn presentations year after year, doing occasional updates. So here is our latest update for the warm season virtual Skywarn presentation. So what we'll go over tonight is how Skywarn operates and why it's really important for us. We'll give ourselves an overview of the National Weather Service in Burlington, as well as giving kind of a glimpse at where the direction of the National Weather Service is headed in general. And then we'll follow that with some safety tips, as well as reviewing some of the storm ingredients, storm types, and our warning system, so you can know how to identify some of those systems on radar and make the best use of our severe thunderstorm warnings and things like that. And then we'll wrap up the presentation with some reporting methods and how to report to us. And then this 5th bullet of the increased emphasis on social science is part of that kind of overview of where the National Weather Service is really putting a lot of time and attention into, and which I think in some ways our Skywarn spotters can help with that effort as well. So let's talk. What is Skywarn? Skywarn is a nearly 60-year-old program that trains people to recognize and report severe or hazardous weather to help meteorologists make life-saving decisions. So these times that we spend in some of these classes, whether in person or virtually, goes a long way into helping us in our operations. I have here this photo of 2 meteorologists at work on radar, and you can kind of see that in their case, they're in a little bit of a fish like a fish tank. There is not really any windows for them to see the outside world. And sometimes that's true of us here, where we do not have a whole lot of time to look outside and see how things are going when we're in the thick of severe weather. So this is something that's important to have these Skywarn observers. Again, why do we need Skywarn? The United States is the most severe weather-prone country in the world, with a typical year bringing anywhere between 10,000 thunderstorms, 5,000 floods, 1,200 tornadoes, 6 hurricanes, usually on the higher end of the spectrum, but anywhere that's from weather-related incidents, either 500 deaths or injuries as a result, 5,000 injuries rather, as a result of severe weather. Severe weather in a year typically costs about $15 billion to the country, with about 98% of all presidentially declared disasters in a year that are weather related. So spotters help because a lot of times the most impactful things to this country is often weather related. So why do we as meteorologists, when we have all of these fancy tools from surface observation sites like the automated weather stations that you see on the right with all kinds of fancy tools, satellite looking at Tropical Storm Floyd, weather balloons that we launch into the atmosphere, radar which continuously scans the atmosphere for precipitation, and all kinds of weather models. Why is it that we need Skywarn spotters when we have all of these different tools in our tool belt? Well, the reason is because they all have their limitations. So no matter how good this technology is, there is nothing that beats good ground truth observations, which is something that a spotter provides to us. As an example of what that looks like, if you live in the Northeast Kingdom or anywhere in the St. Lawrence Valley, you know that it is hard for the radar at Colchester to observe anything that's happening in the nearby area. So I have 4 different tilts of the radar, the lowest angle possible at the 0.5 degree tilt, and somewhere a little bit midway at 2.4 degrees, kind of looking up. You can see that the lowest scan of our radar has a hard time seeing anything that's happening over in the Northeast Kingdom, where a lot of this precipitation is not being observed just because the Green Mountains are blocking the radar beam. However, as you go higher and higher up, the radar is able to see more of the precipitation that's actually taking place. However, when we're talking about things like tornadoes, tornadoes are going to be happening near to the ground. So the fact that radar cannot see near the ground is going to be something of greater importance to the Northeast Kingdom. So again, that's one of the reasons why spotters will be critical, is while radar is seeing what's happening in the middle of a cloud, a trained weather spotter may be able to observe a wall cloud descending from that cloud and report it to us. Based on that report, we can then take that observation and modify our severe thunderstorm warnings, or even issue based on whatever a Skywarn spotter might be observing. So who can be a spotter? Who can be one of these people, these trained, anyone that's trained from the National Weather Service? Initially, again, its roots started with amateur radio, branching out into emergency managers and first responders. But over time, it's grown to encompass researchers, students, broadcast media, storm chasers, and pretty much the general public at this point. So in essence, anyone can be a Skywarn spotter. The only requirement is that you are trained by some National Weather Service employee in being able to observe and adequately report severe weather. So let's talk a little bit about ourselves and what we do, why we do it, and what we hope to accomplish. So we'll go into some detail on why we issue things like severe thunderstorm warnings, or the severe thunderstorm watches, or tornado warnings, and things like that. Our ultimate goal at the end of the day is to protect life and property. The enhancement of the national economy is an extra bonus, but really our goal whenever we issue things like severe thunderstorm warnings, we're hoping to prevent injury or damage to property as a result of those warnings. And ultimately, through that, we hope to create a weather-ready nation that is prepared to respond to weather, water, and climate-dependent events. So basically, we want, whenever we issue the severe thunderstorm watches or warnings, we hope to be understood. So we hope that that avenue of communication is effective and causes people to take the proper precautions whenever severe weather strikes. So it's important to know which National Weather Service office serves you. There are 120 different offices across the United States, and we here at the National Weather Service in Burlington, Vermont, cover most all of Vermont. We actually do not cover Bennington or Windham County in far southern Vermont, but we also have the 4 northernmost counties of northern New York that split up into a variety of different zones there. The hierarchy of the National Weather Service, we are under the branch, we are under the Department of Commerce. That is the main federal umbrella that we sit under. And we are a branch of the National Oceanic and Atmospheric Administration. So we're just a small part of NOAA. And broadly speaking, we here at the field offices, those of us who are at what would be called a weather forecast office, we work for the National Weather Service, and made up of about, again, 120 or so offices with about 4,500 employees in total in the agency. Bringing this all together in a map view, of course, we provide service for all kinds of different regions. So as a result, we have different regional offices that focus on each different part of the United States. We are a part of the Eastern region, which is headquartered on Long Island, New York. And from that, you have each of these different large national centers that spend most of their time doing kind of broader scale view. The Weather Prediction Center, which actually I need to go in and change this name. The Hydrometeorological Prediction Center is modern day Weather Prediction Center. They do the weather forecasts for the broad US. The Storm Prediction Center is where you see all of our outlooks, like whether or not we have a slight or enhanced risk for severe weather. Whenever we post those maps, those come from the folks at the Storm Prediction Center. And if ever you see us talking about whether or not we'll see the northern lights, some of those forecasts will be coming out of the Space Environment Center. So all of these different national centers serve some kind of function for the entire United States. And then there's also divided into different river basins, different river forecast centers. The one that services us here is in Taunton, Massachusetts. And so they service this area, including New York and New England. So they focus on this area of the world, but there are all kinds of other basins that kind of focus on mainly rivers and lakes and streams and the flood threats that come from those larger bodies of water. So once those have been broken up, you have all of the different field offices that encompass different parts of the United States. Here we are up at the Burlington office, covering the almost the farthermost northeast area of the United States. So that's good. That gives you a view of what all of our different offices look like across the United States. And then this is a look, a zoom in to what life is like in our office here at the National Weather Service in Burlington. We are located in the airport in this small little area where we have an open office concept where we can chat about what we're seeing on our weather models or on our radar. We can just shout across the room and say, hey, I'm noticing this. Do you notice this too? So that open communication is key for what we do. And so oftentimes we're working together and collaborating as a team to discussing different severe weather threats or winter storms, or if it's a clear weather day, we may be working on research projects. And so to kind of boil it down, we are using a lot of data from supercomputers, performing billions and billions of calculations. And these weather models will tell us something that's different based on how they're set up. So they are doing all these advanced calculations, and they have different physical schemes. And so they're all going to tell us something a little bit different. And so it's our work as meteorologists to filter all of this down to something that you can understand. So when you get that question of what does a 40% chance of rain mean for your area, modern technology lets us say this literally at this point. Before we were kind of locked into one or two models, but that's not really the case these days. It used to be a little bit of a pattern recognition and things like that. Pattern recognition still plays a part, but now we have multiple families of models, which we sometimes call ensembles. And like a musical orchestra, they're made up of many different parts and components that help make up a whole that lets us account for some of the differences in some of the physics of a model, or even just watching what happens with air over time. So if you've ever heard of the butterfly effect and how if a butterfly flaps its wings in New Mexico, then you get a hurricane off the coast, that's kind of the idea. What small unaccounted features could result in drastic changes to the weather is something that an ensemble is supposed to account for. So with that, they may be made up of 10 members, and if 4 out of 10 of them say it'll rain, then we could literally say there's a 40% chance of rain. Of course, we as meteorologists can work with the numbers and adjust them based on the weather pattern at large, or what we're observing at that moment in time, whether or not we need to go higher or lower. And the technology is still growing. AI and machine learning will become part of the weather forecasts of tomorrow. So they are looking at different parameters that are observed both from the model and in real time to forecast the chances of severe weather in the near future. So this is an example of an event that the AI or machine neural network forecast detected some severe weather potential in parts of the southeastern US earlier in April of this year. So part of that growing, part of the growing process is really working with our mission as adjusting for climate change and social science, really making sure that our communications are up to standard in a changing world, and making sure that we're understood and able to support underserved and vulnerable communities. You may have noticed over the years, if you've lived here for quite some time, that our nighttime temperatures have been getting warmer and warmer, with a greater number of readings that are not falling below 70 in the middle of the night. So there's been a slow but steady upward trend, especially in the last decade, where temperatures have not fallen below 70. Without access to AC, this can be particularly problematic when there is no relief from these warm temperatures. So overall, we're noticing also a slight increase in the number of days over 85 that would make the use of AC more helpful. So that'll be one of the things that we kind of continue to work on, is how do we communicate heat risks in a state that's growing more diverse with time passing through. So especially as we have those of the Hispanic community, or even serving some of the French community that lives in the region, being able to communicate in other languages, and being sure that our social media posts have alternative text for those who may not be able to see what's a very visual media in weather. So being able to serve and warn for each of these areas will be important, because not every area is going to have the same sense of vulnerability. So we want to make sure that we are providing forecasts that are accessible to all and match the needs of those local communities. So some of the ways that you might see that, if I could use an example right now, is our frost and freeze program. You may notice we issue frost advisories just for the Champlain Valley when it's colder in the Northeast Kingdom, or in the Northeast, or in the Adirondacks of New York. Well, part of that is their growing season hasn't quite started yet. And so we have those different criteria for what time of year it is, just to follow the usual climatology of when it's expected to be near or below freezing. Similarly with heat, we're discussing the potential of whether or not we want to have lower criteria in areas like the Northeast Kingdom, where there's greater risk for heat-related illnesses just due to the greater vulnerability of that community. And that's just based off of statistics that come from things like the census from year after year. So part of our motivation with this, with instances like Hurricane Ida, there were a lot of learning lessons that we need to be more proactive in engaging these vulnerable communities. I think part of it will come down to Skywarn spotters being willing and ready to tell their story. I think one of the things that may not be known is that if you have things like wells with which you draw a lot of water, or farming type stuff, you can actually provide reports to the drought monitor. So you can actually tell tell them that you're having impacts from things like drought. And so things like that will become increasingly important in helping us understand the risks that heat poses, or drought, or any number of things, just by willing to speak up and say, like, hey, I've had this weather impact. And I think that'll be something important for spotters going down the road. So we're increasingly emphasizing the importance of things like social science as well, and to really build these coalitions to target our at-risk communities, and be able to provide better weather forecasts overall. I think one of the key things is using the showcase of probability with a not so great forecast that came out of us for March 14th for this heavy wet snow event, where we were well on the low end of snowfall forecasts, but we can still use probabilistic forecasting to at least give the idea of whether or not a user might want to determine if they're willing to risk even, say, a 50% chance of exceeding a snowfall amount. So even if it's not expressly forecast in a deterministic sense, you can use these probabilities to say, well, the forecast may say 3 inches, but if there's still a good chance that there will be over 6 inches, say, in the Burlington area, maybe I'll take precautions to mitigate those risks. So these are things that we can use to help core partners with their operations, and that you can use in your daily life to help with your planning for outdoor recreations and things like that. If you've ever looked at our winter page on weather.gov/BTV, you may have spotted these box and whisker plots that show our forecast relative to the percentiles, which help you see uncertainty and the most likely range of a forecast. So this, again, can help you determine your risk. On the social science side of things, really playing with ensuring that our color scales are consistent so that they're the same across each different threat level is a way to help simplify our communication and match it with like a 5-tier approach so that every kind of thing kind of roughly corresponds with that threat level in communication. And so that'll be a work in progress so that no matter the weather hazard, you can roughly gauge the threat with the same kind of expectation for each different hazard. And so one of the areas that's shown based on what we've received from social scientists is avoid the color green, even in any kind of low-level hazard threat. So we save the color green for when there is absolutely no hazard of any kind of event. Whereas we save the purples for the highest end scenarios. And this map is for when we had that hit and run, very cold air mass that came through in February that brought our wind chills down into the 30 to 40 below zero range. So those are kind of the things that show like, okay, when we're talking more of the extreme level, like this is potentially life impacting. And further down the road, we'll be talking perhaps about things like the vulnerability overview tool, which shows, okay, these areas have been hit by tornadoes like 3 or 4 times. You kind of look based on the overlapping impact areas and say, okay, this area has been hit a lot. We can adjust our messaging because this region may have greater vulnerability due to the recency of impacts from other tornadoes, floods, ice events, or wildfires. And then, of course, as mentioned before, increasingly branching out our social media graphics to be in multiple languages. So these are the things that we're looking forward to down the road. And so even our spotters can help in this aspect by providing feedback. So before we delve into thunderstorm science and things like that, and of course our safety unit, are there any questions about Skywarn, about the National Weather Service in general? Or is there anything else that comes to mind? There is a small little question box there that you can put in some of your questions there, and I'd be happy to respond to them. I'll take a quick sip of water here before we start on the next segment. All right, I don't see anything in the question box for now, but you're welcome at any time to put questions in, and I have several other periods where we have breaks for questions, and when we get to those, I will get to any questions that you put in that question box. All right, so let's go into our safety unit. Of course, the main thing we want to emphasize here is that your safety comes first. Whenever it comes to weather, be aware of the situation. Have multiple avenues of communication available, have an escape route planned in case severe weather strikes, and then when it does, have that safety zone set up so that you can execute your escape route. So your safety should always come first. I never want to hear injury take place by someone going out to try and get a report for us. So never put yourself in harm's way to get reports to us. When thunder roars, go indoors. It's important to respect that rule. There's so many videos that we see on social media of people who really should be walking inside as they're viewing tornadoes just a mile down the road. We want to emphasize your safety. And of course, as we transition into summer, we want to emphasize the importance of heat safety. When we talk about the heat index, that's a measure of temperature and the humidity. And that's what we use to kind of emphasize what it feels like. It's a relatively broad term. It's going to assume that you're actually in a shaded area as well. So even with our heat index forecasts, it may feel even hotter still in the sun. So we issue heat advisories whenever the heat index is expected to be 95 or higher for at least a couple hours. And we go to the higher scale of the excessive heat warning when that heat index is forecast to be 105 or higher for at least a couple hours as well. So know the signs of heat exhaustion. The main thing is that heat exhaustion involves excessive sweating, and heat stroke, the more severe case, is when you stop sweating. Once you start experiencing things like nausea or vomiting, or if your pulse feels weak in the case of heat exhaustion or very strong in the case of heat stroke, or if you're feeling muscle cramps or any faintness, get to a cooler place. And if you get to the higher scale of heat stroke, that's when you actually need medical attention. So when you get to the realm of heat stroke symptoms, you need to start seeking medical attention at that point. But with things like heat exhaustion, that's when you start trying to seek areas indoors and start drinking plenty of water until you feel more rested and ready and more energetic again. With severe weather, pretty much all of these can be summarized by seeking some indoor shelter away from windows. That pretty much summarizes the best place in a tornado, hail event, or severe wind scenario. With a tornado, it's best to be as low to the ground as possible. Higher story buildings, usually roofs are going to be ripped off, and so you'll be more vulnerable to debris. So it's best to be in a ground floor if possible. Knowing that's not always the case, sometimes you can use things like blankets and pillows and wrap yourself around in those to prevent anything from that. With floodwaters, you want to be able to avoid rising waters. Sometimes that means seeking higher ground. Sometimes that means just moving away from any kind of rushing water if you have multiple severe hazards. Usually in those cases, you can use your best judgment. And with lightning, the best thing, of course, is again, to stay indoors. So when it comes to the flood water thing, don't underestimate the power of flowing water. Usually about 66% of flood-related deaths or injuries are going to come from people wading into flood waters. So it's important whenever you see any kind of fast-moving water, it only takes just 6 inches to knock over an adult or carry away children. At 12 inches, it can start carrying away smaller cars, and at 18 to 24 inches of flowing water, you can start to take away larger SUVs and vans. So next up is the kind of communication side of things, how we start to boil things down from a broad scale view, a large scale overview, down to the seconds when those escape routes that you have, it's time to put those in action. So the outlooks occur on scales from days to maybe usually 3 to 5 days at the longest extent. At that point, if we are expecting severe weather, we'll be kind of working with the Storm Prediction Center to assess the threats for our local area. And things like our hazardous weather outlooks. I showed that to you earlier in graphical form for the extreme wind chills. These kind of things can be used to kind of assess your potential in the 3 to 5 day range. When we start talking about severe thunderstorm watches or tornado watches, that's when it's best to monitor conditions where you're on the time frame of hours away from an event. And when we're talking about the warning phase, that's when you have minutes to take action. So when we get down to this point where we're starting to see things like supercells on radar, that's when you may only have anywhere between 5 and 30 minutes to take action. And when you start hearing the severe weather take place, that's when you may have seconds to react. So the Storm Prediction Center, they are made up of experts. They are the authority on severe weather. They spend all of their time researching, studying, and analyzing severe weather events, and determine the potential for whether or not thunderstorms will be just garden variety, popcorn style, no severe weather expected kind of thunderstorms are expected in a day, or whether we would be looking at widespread, long-lived severe thunderstorms. And so you'll see there are 3 different ways to think about it. You have the number system, 1 being least likely to produce severe weather, 5 being the most likely to produce severe weather. Then you also have the color scales that we've mentioned, where the green is maybe less in vogue these days, where you have green meaning a lower chance of severe weather, and this more red and purple color being more likely to experience widespread and strong severe thunderstorms. The other way is through the description, whether it's, say, marginal, slight, enhanced, moderate, or high. So depending on which way best works for you, you can look at the different graphics to assess your severe potential from what the Storm Prediction Center thinks will be most likely. In map form, it looks something like this, where usually the thunderstorm risk is broad, and then as you get more and more focused, you have a smaller area that has some of those higher or moderate severe weather risks. So that's what those look like on a map form, but each threat even has their potential mapped out for each different category of severe weather, from tornadoes to wind to hail, to try and give you a sense of what severe weather hazard they're kind of anticipating on any given day. So your chances for a tornado, wind, or hail case may vary from severe event to severe event. And when we get to the watch phase and the warning phase, it's important to know the differences between the two. We work in coordination with the Storm Prediction Center to issue the watches, whereas we here at the National Weather Service are going to be solely responsible for the warning products. So when we talk about watches, we're talking about conditions that are favorable for severe weather to develop over the coming hours. So that's the time to remain alert. And when we start moving to the warning phase, that's when it's time to start taking action. So again, the watch and the warning. The watch is the alert phase, where you start monitoring information, whether through your broadcast media, local trusted networks, turn on NOAA weather radio, make sure your wireless emergency alerts are on the phone, and start kind of watching the window, seeing how the skies are looking. And when things get to the warning phase, that's when it's important to go to an interior area, preferably at the lowest part of the house, and if necessary, cover yourself in pillows or take the tornado position if necessary. Watches are going to be much broader, covering a large area, whereas warnings are really focusing things down to the minute, and so they're going to follow a smaller area. So both House 1 and House 2 might be under a watch, but House 1 may have just a warning polygon over their area. That doesn't mean House 2 is out of the woods yet. It's just the warning is going to be a more finely focused product. It's important to know the difference, because a lot of times we deal with people confused about the two terms. So the best way to think about it might be in the form of analogy. So if we have any bakers online, we have the cupcake analogy, where a cupcake watch may be having the ingredients present. You have everything that's needed to make a cupcake. So you have sugar, flour, butter, eggs, vanilla, and cream. Everything is prepared to make your cupcake. And the cupcake warning is when you've baked it in the oven, put on the frosting, and prepared it for service. It's imminent or about to be ready for eating. Let's talk a little bit about the difference between a tornado watch and a severe thunderstorm watch as well. Want to highlight this as well, as I think it's important to note, whenever we're talking about the difference between a tornado watch and a severe thunderstorm watch, it's important to know that really it's going to all be based on what the tornado potential is. If the tornado potential is at least moderate, it's always going to be a tornado watch. Even if the potential for severe winds is higher, no matter what, as long as the tornado threat is moderate, it's going to be the type of watch that's issued. On the other hand, if the tornado threat is low and other severe weather threats are higher, in that case, a severe thunderstorm watch will be issued. And that's not to say a tornado can't occur, but the likelihood of other hazards are just so much higher compared to the tornado threat that the severe thunderstorm watch is what's chosen instead. So that's an overview of why that difference takes place. Boiling down to the warning criteria, severe thunderstorm warning is going to be issued when we think a thunderstorm will be capable of wind gusts at 58 miles per hour or greater. That's not to say that a 40-mile-an-hour wind can't knock over trees as well. So sometimes, since we don't have a lot of observation stations that are going to be able to accurately report that, we often take down trees and power lines as reports for severe thunderstorm warnings as well. Now, a lot of we found through surveys that not quite as many people recognize this, but hail is part of a severe thunderstorm as well, where if hail is going to be expected to be greater than 1 inch in diameter, we will issue severe thunderstorm warnings for that as well. A tornado warning is going to be issued when we have high confidence through Doppler radar indicated rotation or from a confirmed report of a tornado taking place. Those types of things will cause us to issue things like tornado warnings. And then the flash flood warning is when we expect things like those 6 inches or more of flowing water that could knock over people or start taking away cars. Those rapid rises in water that particularly require some level of evacuation or avoiding roads. In those cases, we will issue things like flash flood warnings. And then to highlight the different types of hail and wind kind of potential. Oftentimes with hail, it's good to use some kind of common household object. We strongly discourage the use of marbles due to how variable marbles can be. So usually things like dimes and pennies or quarters, or even golf balls, tennis balls, those kind of things roughly correspond to things like an inch of hail, an 1 3/4 inch size hail, or 2.5 inch hail. One thing that I would like to note is that lightning is actually not part of our severe criteria. It is a killer, and we will take instances where lightning causes damage to property or causes injury. We like to receive those reports as well, but it's actually not part of our severe criteria. So it's just the wind or the hail. I mentioned earlier that we don't have too many places to actually observe strong wind gusts. We're not like the open plains that have no kind of obstruction. We have all kinds of trees and mountains that obstruct wind. So oftentimes it's good to use some of the trees that you see to roughly estimate your wind speeds. Usually at about 32 to 38 miles per hour, even that low, whole trees will be in motion at that point. It's usually not until about 39 to 54 miles per hour that you start breaking off twigs and branches and things like that. And usually it's once you get over that 55 mile per hour threshold that you can start doing some damages to structures and things like that. And of course, on the higher end of things, when we hear reports of things like roof peelings, that's when we start looking a little more deeply, because that is usually associated with winds greater than 100 miles per hour. Of course, depending on the structural integrity of the roof as well. So we have a tier-based approach to our storms. We call it impact-based. And so based on that, you'll hear a different kind of, I guess, level of scale or intensity to what kind of language we use in our storms. The base level severe product shouldn't be ignored, but in these cases, it will not trigger the wireless emergency alert system. This baseline severe thunderstorm usually is enough to cause injury, but usually doesn't. It's usually not quite as life-threatening. But things like the destructive severe thunderstorms, where wind gusts in excess of 80 miles per hour, or a baseball-size hail, where you have considerable danger to life and property, where the danger is very imminent, that's when things like the wireless emergency alert system will go off. So over the time, we've kind of pared down so that you're not excessively getting these alerts on the radio or on your phone, so that you're not, say, overwarned for some of these kind of events. So other events that trigger the wireless emergency alert system and that also have a tier-based approach will be tornadoes. So tornadoes also have a base considerable and destructive flag, as well as flash floods, and now snow squalls have it as well. All right, so let's dive into some of the basics of thunderstorm science. At minimum, thunderstorms need three things. Usually when you get to the peak of summer, you can sort of have some moisture and be able to compensate for it with other things, but other times not so much. But usually thunderstorms want some level of moisture. You don't want too much dry air, otherwise you can't really develop any thunderstorms. You want some level of atmospheric instability to allow air parcels to continue moving up. And then you want some kind of forcing mechanism. And that's just a fancy term to say it's usually best to have things like a cold front around to help thunderstorms develop. Usually when it comes to making storms a little more severe, usually you want things like wind shear. Now, a variety of other factors can combine to make storms more or less organized, but generally the more organized, the greater the severe threat's going to be. My turn of phrase that I like to say is the more photogenic a storm is, the more likely it's to be dangerous. So what exactly is wind shear and how does it play a role in thunderstorm development? You have two different types. You have directional shear. So say you have a southwest wind at the ground heading northwest, and as you head higher and higher into the atmosphere, you have more of a west wind. That change in direction is ideal for helping a thunderstorm rotate. So directional shear often helps supercells develop. Now, in the case where the wind is the same direction but increases in speed, that's called speed shear. So usually that creates kind of a rolling motion in the atmosphere. So that's when you see things like shelf clouds or roll clouds develop. And the unidirectional or speed shear is ideal for the development of things like squall lines. And so putting all of this together in map form, we have all of the ingredients coming together for a thunderstorm. Is the sunlight helps to heat up the atmosphere and to allow some level of instability, and different moisture sources from the Gulf of Mexico to the Atlantic Ocean, or even the Great Lakes, along with a cold front moving through the area, provides all the ingredients that are necessary to help produce thunderstorms in the North Country. So with that, before we head into some of the radar signatures and some of the climatology of severe weather in the region, we'll take some time for questions here. All right, I have one question here. Do we have access to these slides afterwards? So I usually put these slides at weather.gov/BTV or Bravo Tango Victor /Skywarn, and in the resources tab, I actually need to go in and put these updated slides in there, but I put the latest warm season and cold season presentation slides in that resource tab. So you can access it on the BTV Skywarn page. And then our wireless emergency alerts for broadcast radio the same as we get on our cell phone? Yes, the wireless emergency alert will also be broadcast on radio as well as the phone. The base level severe events will actually also go on things like NOAA weather radio. So that will have all of the events, whereas the ones that you will get on your cell phone will only have the ones that we tag as particularly destructive storms that have an especially imminent threat for injury or more life-threatening thunderstorms. So for that highest tier of storm, that will get to your cell phone. Excellent. Thanks for those great questions. All right. Not seeing any other questions at this time. So let's go into our overview of thunderstorm types and hazards and how often they occur and when they occur here in the North Country. Our climatological peak for severe weather is going to be during the summer months. And the reason for that is we have more daytime heating that allows for greater atmospheric instability to help air parcels rise. So think of like your convection oven, a little bit of a similar process with helping thunderstorms develop. With adequate heating, air parcels are able to rise, and that rising of air is really important to the development of thunderstorms. So usually our peak severe weather season is going to be the months of June, July, and August. So we go up pretty quickly. It's not unheard of to experience severe weather across the February, March, and April, but really it's a quick ramp up as we head into July. So July is our busiest month for severe weather on an average year. You'll notice that initially there is quite a there is at least a slightly lower, say 422 or so wind reports compared to 152 hail reports in, say, the month of May, whereas the number of wind reports more than doubles, while as the number of hail reports only slightly increases. So the likelihood of hail is a little bit better earlier in the season, partly because the hot temperatures in the middle of July often causes hail to decrease in size or be less possible as you get hotter and hotter in the season. So that's a small thing to note, is the ratio of wind reports really scales up as you get to the season. So one of the differentiating factors between, say, us and a place like Florida is that when Florida gets to summer, weather fronts really don't make it all the way down south. That's part of just how the atmosphere works in summer, as the temperature contrast between the poles and the tropics is just a lot less in the middle of summer, since the polar regions are having so much more sunlight. So as a result, Florida just doesn't get the fronts that often also have some level of wind shear. So we, being up here at the close to 45 north latitude, still get cold fronts in the middle of summer. We also have a good connection often with the Bermuda High that brings in moisture from the Gulf of Mexico northwards. So with good daytime heating, that usually makes July prime for our busiest weather here. In general, most weather is going to take place, most severe weather is going to take place between 1 p.m. and 10 p.m. here in the North Country. And again, that's part of just that solar heating. The sun plays a critical role in helping us develop thunderstorms. And so as a result, most of our severe weather will happen when the sun is up and a little bit less when the sun is down. I will add the caveat, though, that less people will be awake to report severe weather during the overnight hours, but in general, that instability is going to be important for us. Now, if people are waking up to report things like large hail overnight, that's probably going to be because it woke them up as it started taking place. But hail and tornadoes show that same trend of being roughly between about 1 p.m. and 10 p.m. here in the North Country. And looking at that in a map view, oftentimes you'll see hail reported in clusters around populated areas and roads, and less in other areas because we sometimes just don't hear what all is happening at these other parts of the world. So places like the Adirondacks, where there's not a whole lot of people, maybe just some hikers, not going to receive too many hail reports, especially if those hikers are not going to be going out there in the most severe of storms, then we may not receive those reports of whether or not winds, tornadoes, or anything brings down trees or causes large hail in the Adirondacks. But even the Northeast Kingdom, far Essex County, Vermont, we don't often hear things in areas like Island Pond So those kind of areas where there's not really too much population, we may not hear about hail. With wind, it's a little less noticeable, that distribution between population and wind reports, because usually hikers, as they go about their hiking, might say, hey, there's a tree now that's down on my preferred path. So oftentimes we'll have more reports even outside population centers. However, there will still be usually a cluster around more populated areas like Burlington. And then for our tornadoes, even a little bit less of a correlation between population centers. It's really going to be terrain influenced. Variable terrain will disrupt the circulation of tornadoes, which is part of why we encourage things like if there is a tornado occurring and you're outside, to go in a ditch, because that way all of those strongest winds are happening well above you, along with all of that debris. And so for us, there is going to be a little bit of terrain-driven shear as well, just because wind is going to be channeled between the Adirondack mountain range and the greens. So having this area of terrain here between the greens and the Adirondacks, winds are just going to naturally funnel into the area just as they avoid the high mountainous terrain. And so as a result, you get just a little bit of natural shear and convergence in places like Addison County, where we have, this is as of 2016, so this will not account for the tornadoes that have occurred as of late in Addison County, but it's why areas like the Champlain Valley are going to be at least a little bit more prone to tornadoes, as opposed to areas even just on the western side of the lake, where downslope winds from the Adirondacks usually causes sinking air here, which you'll see that there's not been a reported tornado in Plattsburgh. So things like that, it's very uncommon on the west side even, but on the east side, you'll see quite a bit more reports there overall. So our terrain plays a big part in where we expect tornadoes, but of course, there are probably many tornadoes that happen in the forests that we never hear about simply because no one lives there. All right, so let's start moving away from the climatology of severe weather and start talking about some of the signals for it. The best way for us to assess storm intensity is through radar. So radar is constantly scanning the atmosphere, usually in a cycle of about 5 minutes or so for the most part, to kind of give a whole scale view up and down of what a thunderstorm looks like. So it's sending a pulse of energy out. And so things like rain, but even dust, debris, bugs, even trains and cars are reflective of that radar beam. And so they send some of it back towards the radar. And so whatever the radar receives back, if it sees that there's a lot in that area where it's scanning, you can get the idea that there is a particularly intense area of rain where a lot of energy is coming back. So this helps us to determine the location and movement of where the heaviest rain, snow, or if hail is occurring, just based on how much radar energy is coming back from those meteorological targets. And so the structure of a thunderstorm is going to tell us a lot about what we see on radar as well. To give you a quick glimpse of the basic life cycle of a thunderstorm, it happens usually in just about 30 minutes. It starts as, again, that rising motion, that heat takes place is really important. So we're looking for rising air, usually to get above that freezing layer. That's important for the development of hail and cloud ice. And as that interacts with supercooled water, that helps that separation of charge to take place, which is important for lightning. So we want a thunderstorm to at least get above anywhere in the atmosphere that's below freezing. And then at a certain point, it reaches maturity when rain starts to precipitate. That area of downward motion cuts off the updraft over time. And eventually, there's no more updraft. And so as a result, you have no more air that's getting above this area that's below freezing. And so you get no more lightning to develop, and your thunderstorm eventually dissipates. Usually when we're looking for things like severe weather, we're looking for overshooting tops at the point where the updraft is strongest. So here's an image of lightning in slow-mo, or a video rather. So it starts with step leaders that make a connection with the ground. So as charge builds up, there's the different charges are starting to attract, and so the step leaders are that process of that connection being made, and when it is made is when the lightning flash takes place. And so that's when your air warms up to temperatures that are about as warm as the sun, and when that rapid expansion and contraction of air takes place, that creates that sound. And so in reality, it really is like a thunderclap, because your air is basically expanding from that heat and then quickly crashing back in on itself. So that's part of where that idea of the thunderclap gets its name. So usually the distance between lightning and thunder is going to be about 10 miles, but just know that the world's longest observed continuous strike is 477 miles in length. So we really do mean it when we say, when thunder roars, go indoors, because lightning can strike well away from where the thunderstorm is taking place. So we gave an overview of the single cell thunderstorm. The single cell thunderstorm may appear just light and alone on radar, not really associated with any other storm. It's kind of its own separate entity on radar. Of course, even a single cell thunderstorm can develop into something like a supercell in the right atmospheric conditions. So usually this is to say there's less to really organize the storm. There might be more dry air in place, but this is the general look of a single cell thunderstorm. And this is the look of a supercell, which is going to be a lot more organized. Looking down at down the page here, where we're getting into more widespread thunderstorms, you may have something more disorganized, these kind of amorphous, less structured kind of thunderstorms that have several tall towering cumulus in the horizon, but may not have too much structure. They may drop out features like gust fronts, where the downburst of a thunderstorm will kick up things like bugs and dust and debris, and that's slightly reflected by radar. And so usually you can see these, they're like microscale cold fronts in a way, that help you determine where new areas of convergence might happen, where say you have inflow into this area of the thunderstorm that's meeting this little gust front, and you can expect new development to take place where air is coming together in those spots. And then, of course, further on the right, we have features like squall lines. Squall lines are going to be a little bit more organized, but follow the same principle as having different clusters of thunderstorms organized together. And at the more extreme ends, we'll have mesoscale convective complexes and vortexes that have little bookend vortices, things like this feature that's tracking just north of the Albany radar over here. And so this forms as you have air that's moving somewhat fast at the center and gets slower and slower and slower, and that just naturally creates a little area of curl at the north end of an area at a line of thunderstorms. And usually, because this is an area of curl, this might be this spot where you might expect some kind of tornado to take place. So basically, the thunderstorm environment creates all different kinds of structures, from thunderstorms that are just off on their own to highly organized systems. It all depends on the storm environment, and radar gives us a clue of what a thunderstorm is capable of, and we can kind of get a sense of what might be happening even just within the environment based on some of these radar signatures. And a storm structure can evolve over time, where single cell thunderstorms may merge, coalesce, and then become a squall line. So this is an event that happened just 5 years ago on May 4th of 2018, where we had a high-end severe event, which consisted of thunderstorms that started developing in northern New York that became more organized as they came across Vermont, New Hampshire, and Massachusetts, causing lots of wind damage. as this line went through. So over time, the storm structure can change, and again, that can tell us a lot about its severe potential. This is what severe winds kind of looks like on radar in a single cell thunderstorm, where wind is, so radar again is telling us the motion of a thunderstorm. So it can tell us when winds are coming toward the radar, which is noted here in the green color, and away from the radar, noted here in the red colors. So based off of this, we can see if in the same line of a thunderstorm, wind coming toward the radar and away, that right in here, some kind of downburst has taken place. Usually they're not of the strength to produce this kind of image, but overall, they'll usually knock over maybe a few trees, maybe some power lines at that. But some of the extreme cases will look like this, where you have the epicenter take place for your downburst, and then the air has nowhere to go but out. And so what it does is over time, it just expands and broadens out. And you can see that that kind of signature with all of the trees toppled in the same direction, just following the outflow of that downburst. And then next on the scale, or rather how this kind of takes place, we mentioned moisture as being important to the process of developing thunderstorms, but even dry air has a part to play when it comes to a downburst. I'll even note today, we were watching a shower that developed in New Hampshire and caused a 33 mile per hour, or actually it was a, sorry, not 33, but 36 mile per hour wind gust in Concord, New Hampshire. Even though it was not producing any lightning, it still produced a strong wind gust because of the role of dry air. So that dry air moving into a thunderstorm helps that process of evaporative cooling to be more efficient and results in a stronger downburst. So things like dry air can be critical to helping us as well assessing severe potential. With straight line winds, part of the essential process of this and seeing it on radar is seeing what the image of precipitation looks like on the backside. Where if we see features like this, where there's a lot of reflectivity on the backside of a little line right like this, and a little bit less on the northern side, we can infer then that the rear inflow jet is moving into this part of the thunderstorm. So the strongest winds would be expected in this region, and we can use that for the sake of our warnings. Straight line winds, named mainly for the fact that they produce wind damage in a straight line. So the name, I guess, is very appropriate to the threat. But in general, again, like a downburst, all of the trees will point in a singular direction from a result of straight line winds. And if you've ever wanted to know the jargon term for it, we meteorologists will sometimes call the squall line the quasi-linear convective system. They are still capable of producing tornadoes, usually in any of these areas where breaks occur or where there's some kind of bowing. So something like this little part right here, where it kind of bends just a little bit, this area might be a little bit more prone to a tornado than perhaps another part of that line segment. And then looking at the derecho is the kind of extreme case of this. So you need really extreme instability, and you usually need very high shear. The derecho is not named for the wind, but rather is just the event of these handful of hurricane force gusts that extend over, I think it's somewhere on the order of like 400 miles or something to that effect. But these are particularly strong straight line wind events, and they can also include tornadoes. These little red dots here are areas of tornadoes, kind of like we mentioned with that bookend vortex at the very top of the right hand. This little area is where tornado development is most likely in these kind of areas. But this particular event, you can see it happen really early in the morning. And as a result, it caught many hikers off guard. And I think it did something on the order, it's estimated that perhaps I think 2 million trees were damaged across thousands of acres as a result of this derecho. Fortunately, they only occur once every 4 years or so. There have been some suggestions this climatology needs to be revised. It may be actually less than this, but in theory, we are actually due for one in the we haven't had one in quite some time here. So hopefully it won't happen this year, but usually about once every 4 years. So that summarizes all of the different threats related to wind. Let's talk hail now. Hail is going to be more likely when your updraft is strong and the freezing level is low, so you have less time to melt the hail as it gets down to the ground. And it's going to be more likely the longer the thunderstorm lasts. So a thunderstorm that lasts only 30 minutes is only going to be able to produce hail that's so large. So usually we want to see longevity with these kind of thunderstorms. So the process again of supercooled water moving up that's into this air that's below freezing, and then kind of cycling in and out of that layer is critical to making larger and larger and larger hail. If ever you have a chance, I'd encourage you to cut open a hailstone so that you can see all the cores. It makes all the different rings as a result of cycling in and out of that thunderstorm. And so what that does as well is hail reflects a little bit differently compared to raindrops. It actually sends some of the radar signal back down to the ground, back up, and then it comes into the radar a little bit later. And so as a result, it creates a hail spike where it looks like this little feature here is lagging behind the main area of the thunderstorm. But this is actually erroneous data. There is nothing here. It's just a result of the different scattering regime of hail. And so usually when we see like these purples and whites, hail is extremely reflective, especially when it has a lot of rain associated with it. So those are kind of the ways that we can detect hail on radar. And supercells are going to typically create some of the largest hail because of the fact that they separate their updraft and downdraft by the fact that they're rotating. So the fact that they last longer and that there is the separation allows for larger hail in supercells. Now, a supercell is named not so just because it is particularly weaker or stronger than a regular cell, but is named just for the fact that it is rotating. So when that spin is observed high in the thunderstorm, that's when we call it a supercell at that point. Now, the tornado threat is highest in a supercell, but even out of all supercells, only usually about 1 in every 5 will produce a tornado. However, its signature is quite iconic, the iconic hook echo. So what's happening is you have a precipitation-free area of inflow into the thunderstorm, and where that inflow is most favorable, where that's taking place, you'll have your strongest precipitation then just downwind. So you have your area of hail. The V notch indicates the flow of air in the thunderstorm is help kind of ventilating the thunderstorm. And then this area of this debris ball is not actually precipitation. Remember, we noted that things like dust, bugs, any kind of debris or tree damage, roof shingles, things like that will be reflected by the radar. And so this is actually not precipitation, but it's actually debris that's being lofted by the tornado. So you have the area of the downburst as well that's rotating on the backside here. And so this area is just naturally prone to developing this area of spin that produces the iconic hook echo that we all know. And so this is another schematic view of what that looks like. Again, the wall cloud and where your tornado is most likely to develop is going to be somewhere between the area of precipitation occurring and where there is a lack of precipitation. And so really looking for where that warm air is rising in, and then you have some level of rotation taking place within that thunderstorm. And then precipitation down near the ground is helping creating this area of spin that again gives it that iconic hook echo appearance on radar. So with this, I would like to stress the difference between a shelf cloud and a wall cloud. So a shelf cloud, kind of going back to our schematic here, note that the wall cloud is going to be a very small part of the thunderstorm, whereas a shelf cloud is going to be much larger, extending across the entirety of the horizon. So usually with these, you're looking at the potential for straight line winds. You have that unidirectional wind shear that usually creates small turbulent eddies at the front of the squall line. That gives it this look over the entirety of the horizon. A wall cloud is going to be just a small feature, just like note how much of a smaller percent, like this isn't even looking across the larger horizon. It's a much smaller area encompassed within the wall cloud. And you will be able to note rotation taking place. And of course, you're looking for it to descend closer and closer to the ground. And another view of that, the roll cloud develops as a result of the gust front from that cool rain cooled air coming down, interacting with warm inflow ahead. And this is an example of a roll cloud that went through Colchester in 2008 that has that very distinct appearance where you have pretty much unobstructed visibility to, you can tell it's raining hard behind this roll cloud here. So you can know you're in for heavy rain and very strong winds whenever you see features like these roll clouds develop. And of course, we didn't really go too much into the tropical cyclones, but we are getting into the tropical season soon. But these work a little bit differently. We talk about wind shear as a prime factor for a lot of these different systems, but with tropical cyclones, they actually do not want wind shear. They do not want any friction with land whatsoever. They really are driven by warm rain processes that really help convection to sustain itself even long into the overnight hours. And so this results in very small drops of water, but they're very numerous in count, and so it makes for very high rainfall rates. Well, they can cause isolated tornadoes. With these, we really focus on wind damage and storm surge for the coastline. And then here in places like New York and Vermont, we'll really focus on the flood potential. So they can produce lots of rain that really can result in things like flash flooding or even river flooding in some cases if they come at the right time of year. So with that, that's the basis of this. They're very concentrated areas of thunderstorms that are essentially the most intense convection that occurs within the eye wall. But then you have these little rings that develop further and further out from the center. Just from these, if you can kind of see in the schematic, each area of thunderstorms is going to have a small area of downward motion in them. And so that's how you'll see structures like these different rings in a hurricane. So this is Hurricane Ike. And so with Ike, you can even see just area of roughly more precipitation and less precipitation in certain parts, just based on where that's occurring. And then of course you have the satellite presentation where you have the eye that's developed in this area where there is intense downward motion at the very center, and that air is then expanding outwards. And again, that's part of why the eye wall has some of the most intense convection associated with it. All right, so we've talked all kinds of different thunderstorms. We've talked about hail, wind. We've talked how supercells are different from the average thunderstorm based on that rotation. And of course, the tropical cyclone. Before we move into the segment on tornadoes, are there any questions out there? All right, not seeing anything in the question box at this time. We'll start speeding up the presentation here as we're in our last 15 minutes. Let's talk quickly about tornadoes. Tornadoes are violently rotating columns of air that are in contact with the ground. Fortunately, in this area, they are rare, taking place about once every 2 years in the Burlington area. The main distinction between a tornado and a funnel cloud is going to be whether or not they're in contact with the ground. So as long as it's not touching the ground, it's simply a funnel cloud. But once it is in contact with the ground, it will be lofting up debris at this point. And so once you start seeing things like debris being lofted, you can be confident that this is in contact with the ground. And at this point, we can classify it a tornado. The tornado has many lookalikes, sometimes from a kind of the trick of the light, sometimes at the edge of a rain shaft. It can almost look like there might be some kind of tornado here, but it's mainly just from precipitation associated with a downdraft, kind of expanding out at the edges, and oftentimes it develops even a little bit of a curl at the very edge of it sometimes. So that can sometimes catch people off guard when looking for tornadoes. The other thing that kind of catches people off guard are things like convective debris. This is an example of an image that we got in near Messina, New York, where we had a report of a funnel cloud, but analysis of radar, the expected environment, and the just the picture, this did not look like a funnel cloud. You can see it's kind of ragged looking. A wall cloud will usually look fairly organized and won't look that ragged. One thing you'll want to see is this feature moving up into the cloud, or do you actually see dissension? So things like convective debris will often be lifting up into the cloud, and so that can help you distinguish this. So you can ask yourself that question, as well as whether these clouds are rotating. And if ever in doubt, feel free to ask us. Usually a video is the best thing to send to us. Usually with things like video, we can see that rotation taking place. Whereas with photos, it's a little bit harder to determine. On the weak end of the spectrum are your EF0s and your EF1s. They make up 80% of all tornadoes, but make up less than 5% of tornado deaths. Their lifetime is usually short, and usually as a result only lasts up to about 3 miles. Their wind speeds are about 65 to 109 miles per hour. So I will note that sometimes your strong downburst winds may be stronger than that of a weak tornado. So never underestimate downburst winds as well, as they can be just as strong as these low-end weak tornadoes. And most tornadoes in the North Country here in northern New York and Vermont are going to be in this EF0 and 1 category. On the higher end, you have strong tornadoes, the EF2s and EF3s. Roughly 1/5 of all tornadoes will be EF2s and 3s, and account for less than 30% of tornado deaths. With the more favorable environment, they'll last a little bit longer and have a path of about 15 miles. These stronger winds, up to 110 to 167 miles per hour, will be enough to move cars, affect small mobile homes, and things like that. And then the violent tornadoes, only 1% of all tornadoes are EF4s and 5s, but they will account for 70% of all tornado deaths. Partly, this is due to the favorable environment, allowing them to last a long time, and also have a long path length of over 50 miles. However, the wind speeds of 168 to 234 miles per hour will be able to level almost any structure. So there is not much to protect from these most dangerous tornadoes, and as a result, they will often cause the highest number of deaths. Again, hopefully we will never have to deal with these here in the North Country, but the main strategy for this is encase yourself in pillows and blankets to protect yourself from any kind of debris that's flying around. So that can give you at least a little bit of a cushion from any of those impacts. So before we talk flash flooding, do we have any questions on tornadoes? All right, for the sake of time, we'll move on to flash flooding and what causes it to take place. There are several factors that can come together. Like if we've been dry for a long period of time, we may not be quite as likely. It's all about, if any of you are engineers on here, it's how much is going into the system versus out of the system. So if more water is moving into a river than can leave it, it's going to naturally make it more prone to flooding. A flood is going to be when this process is gradual and slow. Usually these are nice and predictable. However, flash flooding is when the process is rapid and less predictable. It's something that's a little bit more dangerous as well, as water quickly moves into the system and is unable to go out. Again, the key difference is, will water rise quickly and flow fast, or is it going to be gradual? I have an example here of the White River in April of 2019 from snowmelt and rain bringing it to flood versus this ice jam that took place in 2018 on the AuSable, the east branch of the AuSable River, where rain, snowmelt, and warm temperatures caused this river ice to break up and then eventually jam. And you can see just how fast the water rises as a result of that taking place. So ice jams in particular are some of our most severe flash flood events that can take place in the area that unfortunately also often drives people out into the cold as well. Very dramatic instance. I'll let that play through one more time there. So you can get a look of that process of this rotten ice. You can see it's all kind of, you can kind of see the river flowing in a very constricted area and then just rapidly breaking apart and jamming into place. And then once the jam releases, it just, everything flows and your water starts to rise as well. So flooding is going to be most common in the North Country for one, the spring snowmelt part of the year, usually peaking in March. And of course, that's also when river ice is going to be breaking up and impacting the region the most. But also June, July, and August as a result of thunderstorms, or perhaps even tropical cyclones as we get to this point of the year. And as we get into the months of November, once vegetation goes into dormancy, trees aren't sucking up as much water as they do in the summertime. So by the time you get into November, there's a lot more runoff that can take place as well. So occasionally we can get flash flooding in the month of November as well. So of course, the main safety message with any kind of flooding is to never underestimate the power of running water. You may not even see it, but it may wash culverts beneath roads. And so you may not know what's going on underneath all of this until all of that water's cleared the area. So you can see that process of water flooding this road, and underneath it's washed out this culvert, but you wouldn't see it until too late. So you may not know, again, how much water is really there. So especially if you cannot see the stripes on the road or anything like that, turn around, don't drown. Again, nearly 2/3 of flood-related deaths are from driving into floodwater, so I can't emphasize it enough. Let's briefly talk about the marine forecasts and forecasting winds on Lake Champlain, especially as we start our boating season, as everyone's getting back out on the water. Often it's nice to know what the forecast is like on the lake. It works a little bit differently than on land, and the main reason for that is going to be that there is less friction over water than there is on land. So you have just more trees, more mountains. Water is more flat, uniform, less friction compared to land. And so the winds tend to be greater on the lake than over land. So the process of the fact that water warms and cools much slower than air often plays a role as well. And so with marine forecasting, it's all about mixing potential. How unstable is the atmosphere above water compared to land? And then we also have channeled flow here. Winds will accelerate through the Champlain Valley through the Bernoulli principle. You can see our favored winds are through this wind rose, that most of our winds will be out of the north, south, or southwest. and that's going to be as a result of the Adirondacks to our west and the Greens on the east side that forced wind into this favored north-south pattern. And so mentioning the seasons and how that affects the stability over these larger bodies of water, the water is going to be a lot slower to respond to change in temperature than air. So during the winter season, the sea surface temperature or the lake temperature will be relatively cool, where we might have a blast of Arctic air that results in unstable conditions because the air is colder than the water. However, as we switch seasons, now heading for spring and into summer, we can start warming into the 70s to 90s, but the water temperature at this point in the year is going to be colder, anywhere between about 50 to 70 degrees. And as a result, will be stable. And so the winds tend to be weak this time of year and make it great for recreational boating. However, as we switch seasons back to fall and start getting some of that cold air back into the region, our winds start to become more unstable again. So to see that in graphical format, I have the frequency of 25 knot gusts, or winds that are about 28 miles per hour, where you have, I have marked here the primary time frame of strongest winds between mid-March and mid-September, or I should say mid-September and mid-March, whereas the period of lowest winds is usually about this time of year, heading into June and July. Becomes a lot less common, but we can still get those strong wind gusts when we get things like thunderstorms to roll into the area. So that's just a glimpse of marine forecasting and things like that. Again, for the sake of time, I might just go on here into the reporting segment here. So again, feel free to be asking any of those questions in the question box, and we'll answer those as we get towards the end of the presentation here. Just a few slides left on how to report severe weather. An effective spotter is going to report and answer the following questions. If you make a phone call to us, we're probably going to ask first, where are you located? Because of course, sometimes we can get a sense of where a caller is calling from. We usually have an idea of, oh, this person's likely in the Burlington area based on the caller number. But that'll be the first thing. We want to be able to tie what you're reporting to what we see on radar. So where is going to be the biggest factor? What time it took place is, again, important to matching it to radar. And then how long it lasts can give us an idea of its severity. And then, of course, who are you? We will not know all of our spotters heart to heart, so let us know who you are, that you're a trained spotter is usually an important part. Of course, also calling on the toll-free spotter line will also identify you as a spotter compared to a member of the general public. When reporting things like hail, it's important to measure it fast. That hail is melting, especially if it's going to be in the 90s. Want to make sure that you get that hail measured as fast as possible to get an accurate measurement. Measure from tip to tip, and usually it's good to have a photo for verification. So especially if you're looking to beat this record hailstone that took place in one of our employees' own backyards, that you can verify that for state records. And it's also helpful for us to verify as well. The best areas to report are through the spotter line. This toll-free line can be used for spotters to be able to give us information without going through the phone tree. Social media, we may not check social media on the most active weather. We may not have the time, but you can report to social media. We usually are tuned to the white-face repeater. So if you're tuned into the 144.51 megahertz, we'll be listening to that. We have a storm report page to use as well. And there is a crowdsourced app called InPing as well. And we encourage sharing photos. Additionally, if you are interested even in reporting weather beyond Skywarn, there are also more committed programs like Co-op and CocoRAS, which play a more important role into mapping out different severe weather events or snowfall events especially, or how much rain took place, that go into broader climate data sets and are considered and treated more official than even a trained public report. So it's best to have NOAA weather radio at hand, have some way to get reports through, say, phone, some kind of media outlet or broadcast. Just having multiple ways in case one system fails is recommended. So that way you can get reports whether from family or friends, social media. There is even a text or email service that you can sign up for. I can't recall where to find it off the top of my head, but you can actually sign up for emails from NOAA if a severe thunderstorm happens in your area. And of course, you can use weather apps or mobile.weather.gov. NOAA actually does not have an app, so mobile.weather.gov is our best attempt to put our website in an app-like format, which you can bookmark. And this is what MPing looks like. It's most useful for changing precipitation types, where we have freezing rain, changing to sleet or snow. And that way we can get a sense of changing precipitation types in those kind of scenarios. So in summary, a reliable Skywarn spotter will provide important ground truth information. We have all kinds of fancy tools and technology, but the radar satellite, they can't see things like downed trees or lines or hail that's on the ground. So a spotter is going to be able to provide important information that helps us verify our warnings, update our messaging, and be able to just kind of tell ourselves confirm, okay, radar says this is big. We have people on the ground telling us that that's true. Sometimes we're cooped up in an area without windows, so spotter reports are really, really important. Storms come in a variety of different flavors. The more photogenic, often the more dangerous that they are. Looking for things like wall clouds, shelf clouds, or overshooting tops can give you an indicator of its severity. On radar, you can look for things like lines or bow echoes, or even artifacts like hail spikes. For our time of year, in summary, our severe weather is going to be most likely in June, July, and August. That's usually the bulk of our severe weather. So we're about at severe weather season, so we'll be relying on our spotters over the coming months to be able to provide us all this kind of information. And at the end of the year, if we have a large number of spotter reports, I do like to highlight those when we get to Skywarn Appreciation Day in December. So overall, your safety should come first. Please do not put yourself in harm's way to get reports to us. I can't emphasize that enough. I never want to hear of an injury taking place from some spotter trying to get a report to us. And of course, it's important to be as specific as possible. We are wanting to know where you're at, because we may not be familiar with your roads and cities. So being able to reference things like landmarks and intersections, or even having a latitude or longitude at hand really goes a long way into helping us pinpoint where the most active weather is taking place. So thanks everyone for attending. Thanks for your kind attention this evening. If you are interested in becoming a spotter, feel free to email me, and I'll also have that information that should go out whenever this presentation is concluded. You should get an email from GoToWebinar thanking you for your attendance. And if you are interested in becoming a spotter, let me know. And also, if there's anything else I can do, I'm always happy to answer questions, take feedback, or just field any kind of questions. My email is open well, maybe not quite any time. We work rotating shifts, so we work odd hours. So it may not be normal business days that we respond, but feel free to shoot us an email anytime. There are all kinds of different ways that you can provide reports. At the end of the day, having a name, an address, and a phone number is usually helpful for us to match our spotters, especially since most people will be reporting from places like their home or where they kind of work. Those are usually the most common areas. So all of these different resources are available for reports, and it's completely voluntary. So how much you interact with us is entirely up to you. But part of me has lately been toying with maybe something more of like a newsletter type thing. I know we do that with Cocoa Raws, and part of me is wondering even if maybe Skywarn should have something like that, but who knows. Anyway, thanks again everyone for attending. I do see here, I'll answer some questions here as we start closing out the session here. We have a report or a question that a Long Lake spotter will report into Albany. Let's see, is Long Lake one of the Finger Lakes? If it's, actually go here. Hamilton County. Yeah, if you're in Hamilton County, Hamilton County is in Albany's area. So I'm happy to pass your information along to NWS Albany that you attended, and they can get you signed up in their spotter network. Each National Weather Service office is going to operate their own Skywarn program. So that'll be the best area for that. Paulette, as far as Paulette, Vermont is concerned, that should be in, I believe that's just in our area, just barely. Yeah, so being in Rutland County, that would count for our area. So yeah, I've had this happen from time to time from people from Arkansas to the West Coast getting onto our Skywarn presentations. Still, thanks for coming. I know it's a lot more of a New York and Vermont focus, but again, I can pass along your information to the National Weather Service in Birmingham, Alabama, that you attended. So we can. They may have some differences in how their program works. So I'll get you. I can get you in contact with their Skywarn, the person who's responsible for managing their Skywarn network, to get you involved. All right, I think at this point we will close out the meeting. I'm not seeing any additional questions rolling in at this time. I want to thank everyone again for attending, and thanks for your attention tonight. Hope you have a wonderful night, and have a great day. Bye-bye.